everyone. You can start.
Okay, thank you. First of all, thank you very much for the introduction and for giving me the opportunity of presenting this research in this very nice seminar. So this talk will be essentially divided in two parts. The first part will be a sort of introduction with a review of what is known about equilibrium states for quantum theories. And then in the second part, I will present some new results. And the new results I will present are obtained in collaboration with Nicola Drago, Federico Faldino, and João Braga Vasconcelos. But let's start with the main matter. So I will use algebraic methods to describe the models I'm interested in, and let me motivate this choice. And actually, we all know that when we have to model some physical theory, what we have really to describe is the result of experiments. Our models need to be predictive. So we need to be able to associate to an observable and a state an expectation value. And usually in ordinary quantum mechanics, the states are described by a ray in some Hilbert space, or more generally by some trace class operator in this Hilbert space. And observables are usually self-adjoint elements, self-adjoint operators, bounded operator acting on this Hilbert space. Unfortunately, when we are discussing quantum field theory, this point of view is not so nice. And that's because very often inequivalent representation arises when you try to do quantum field theory, especially when you consider your quantum fields on infinite domains. And this is, for example, the case when you want to describe the interaction picture. And by the ACT theorem, we really know that this interaction picture doesn't exist. But even for free field, if you consider free field propagating on a flat space-time, and you consider different states for the fields, actually these different states give really origin to inequivalent representation. So when we discuss quantum field theory, it's a bit better to revert the point of view and to start with observables and to consider them as element of a C-star algebra. And of course, in the product of this C-star algebra, we will have to insert the information about the commutation relation and so on and so forth. And this abstract C-star algebra is a bit abstract up to now, but you know that when you have a state which is a positive normalized functional over this algebra, then you have a powerful construction which permits to obtain again the standard point of view. And actually, if you have a state acting on an abstract C-star algebra, by the Gelfand-Naimark-Siegel construction, you can really represent the element of your algebra as bounded operator over some Hilbert space. This pi is the representation here. And then you have also a cyclic vector in your Hilbert space, which permits to describe the expectation value in the standard form. And for our purposes, what we need also to have is time evolution. We need to be able to describe time evolution in this system. And at this very abstract level, the time evolution is just a one-parameter group of star isomorphisms of our C-star algebra in itself. And when you have one of these C-star algebras together with a time evolution, you have really what is called a C-star dynamical system. And this C-star dynamical system is really the basic setting for describing things in statistical mechanics. And now we will go on and we want to describe how to form the equilibrium state in this system. And let's start working in a representation. And suppose that in your representation, the one-parameter group of isomorphism is really described by a one-parameter group of unitary operator. And suppose you have also the generator H of this one-parameter group. And now it happens that if e to the minus beta h is trace class, you can really give meaning to to the Gibbs state. You can construct Gibbs state simply considering this density matrix. And this density matrix represent in practice the canonical distribution of states in canonical systems. So this is really the starting point for describing equilibrium situation. And this parameter beta here represents the inverse temperature. Unfortunately, this point of view is not suited to describe equilibrium states for fields which propagate on infinite system. Actually, even for free field, in this case, if you work in the representation of the vacuum, for example, and you try to construct this object here, this is not really a trace class operator. You can really realize that the traces of this object diverges. So we need to have another way of characterizing equilibrium. And we can do it using the celebrated KMS condition, the Kubo-Martin-Schwinger condition. And here I have reported this, the definition essentially. And according to this condition, you have to analyze this kind of function, and this kind of function needs to be analytically continued in the strip where the imaginary part of phi is contained in 0 beta. And at the boundary, this function needs to be continuous. And if you evaluate things at the boundary, a condition like this one must hold. And it's interesting to notice that if you consider Gibbs state, and if you characterize KMS state with respect of the same time evolution, actually this condition really characterizes Gibbs state. You get exactly Gibbs state from this condition. However, as you can see, this condition does not make use of a particular representation. So it is just an algebraic, essentially, relation. And so somehow this KMS condition is more fundamental than the Gibbs condition. And it can be used also at thermodynamic limit, namely when the system is described on things propagating on infinite amount of spaces. So from now on, we will characterize equilibrium state by this KMS condition. And now, what we want to do here, we want to consider various KMS state, namely various states which are equilibrium state with respect of different time evolution. So we start learning how to construct equilibrium states of perturbed time evolution. So from now on, I will consider a time evolution tau of t, and then I want to perturb this time evolution with a bounded element of our sister algebra. And the perturbed time evolution is actually intertwined with the original time evolution by this object here, where this u of t is a cocycle, which is really respecting this relation and really describes the connection between the two time evolution. And the infinitesimal generator of this object here is this perturbed Hamiltonian. So when we are in this system, and if we have a KMS state at inverse temperature beta with respect of our original time evolution, there is a nice construction given by Araki in the 70s, so a lot of time ago, which permits to reconstruct an equilibrium state for the perturbed time evolution. And the formula for this reconstruction is really this one. And as you can see here, you have in this formula this expectation value of phi I beta. So you are allowed, because of the KMS condition of the original state, to compute the analytic continuation of this object here. And then you can evaluate it at the boundary in this way. And in this way, you really get a state which is a KMS state with the perturbed time evolution. So this theorem permits directly to construct equilibrium state with perturbed time evolution, starting with an equilibrium state of our original system. And the object here have a direct physical meaning. For example, this omega ui beta is really the relative partition function, and so its logarithm up to a rescaling by the temperature is really the free energy of our system. But now there are a couple of very interesting results which have really physical meaning, and which make also physical meaning to this KMS state. Actually, it is possible to notice that some stability holds for this KMS state. And in practice, It happens that if you have some clustering condition plus some other condition, technical condition on the state, it happens that if you compose a KMS state with a perturbed time evolution, and if you wait long enough, the state becomes really in the limit, an equilibrium state for the perturbed time evolution. This is really the Araki construction we have seen before. So in this, in some sense, this means that the time evolution is so strong that wash out all the details of the state, and what you have at the end is really an equilibrium state for the perturbed time evolution. And it happens also the opposite thing. If you consider the perturbed state, the KMS state, the equilibrium state for the perturbed time evolution, and if you compose it with the free time evolution and you wait long enough, well, what you end up with at the end is really the equilibrium state for the free time evolution. These results are very important and tell us that these KMS states are really stable under perturbation, at least under thermodynamical perturbation. This kind of result have been obtained in the 70s and in the 80s by these renowned scientists. And our aim in this talk is really to check how much of this construction I have presented up to now can be reobtained when we work with quantum field theory. And in particular, we are interested in discussing interacting quantum field theory. Okay. And unfortunately, what we will have is that the algebra of observables for quantum field theory will be no longer a sister algebra, but we will have to work with star algebras. And above all, we will take care of the interaction using perturbation methods. So this means that the fields will be described as formal power series in some coupling. And so this is the model I would like to discuss here. We will consider a Lorentzian spacetime. Later on, this spacetime will become flat, but a lot of what I will say in this first part of the talk can be given also for a generic Lorentzian spacetime, so I prefer to keep it generic for now. And the Lagrangian, and I am considering a scalar field, and the classical Lagrangian of the system I am considering as this form. So as you can see, there is a quadratic part in this Lagrangian plus a more than quadratic contribution, which is somehow the responsible of the nonlinearities in the equation of motion associated to this Lagrangian. And so what happens is that a direct construction of the algebra of quantum observables is not available for this system in 4 dimensions. There are, I think, on the market, real construction of these algebras only in fewer dimensional situations. For example, as an example, I want to mention the Sine-Gordon theory in 2 dimensions. And the strategy we will follow is this one. We will divide this Lagrangian in 2 parts. We will consider the free part, namely the quadratic part, and we will then consider the interaction Lagrangian separately. And so the first step will be the construction of the quantum theory, of the free quantum theory, and then we would like to represent at algebraic level the interacting fields as power series over this free theory. And in the power series will be a power series in this parameter lambda, which is the coupling constant stored in the interaction Lagrangian. And of course, in doing this, we will encounter many problems. There will be some problems of ultraviolet nature. There will be some problem of infrared nature. And there will be then some problems with the convergence of the series. And actually, if we look at this power series, and in order to construct something reasonable and in order to get rid of the infrared problem, we will add a sort of cutoff function to this interaction Lagrangian. And eventually we will try to remove this cutoff at the algebraic level. And if we do this, we will still have some problem at ultraviolet level. Nevertheless, as we will see in short, this ultraviolet problem can can be understood also on a generic Lorentzian spacetime. And the problem which we cannot really cope with at the moment is the convergence of this series. Actually, we know in many cases that this series will not converge, and actually this will be simply a sort of asymptotic expansion in the best case. Nevertheless, the other two problems we have can be really understood. So let's start seeing some details of this fact. First of all, I would like to briefly discuss the quantization of the free theory. So in this part, I will set to 0 the coupling constant, and our Lagrangian will be described by this quadratic objective. And if we look at this system, the classical problem associated to this Lagrangian is completely understood. And if our space-time is globally hyperbolic, we will be able to determine unique, retarded, and advanced fundamental solution of this system. And these are solutions of this kind of equation where f is a compactly supported function. And in particular, here I have drawn a little cartoon to describe the domains of this object. So if I apply the retarded propagator or the retarded fundamental solution to a compactly supported function, I will get a solution of this equation which is supported in the forward, in the future, in the causal future of the support of the function f. Conversely, if I will apply the advanced fundamental solution to this other compactly supported function, I will get again a solution of this equation with f twiddle now at the place of f, and the support will be contained in the causal part of the support of f twiddle. And I can immediately select the observables of this system, and the observable of this system will be, for now, understood as sort of functional over smooth field configuration. And the important notion in this kind of functional is this coefficient an. For now, this an will be some smooth function, and they need to be symmetric. And if I equip the system, the set of all these observables, which I call regular, with an involution described by a complex conjugation, and if I add information about the product of this system, I will really get a star algebra. And this star algebra will be the star algebra generated by linear fields, essentially, and the product of this algebra is here in short described by this formula here. Here it's denoted with this star. And actually, as you can see in this product rule, what really enters is only the retarded minus advanced fundamental solution, which I call causal propagator of the theory. And actually, if from this formula, I'll try to understand the commutation relation of two linear fields, I really get the canonical commutation relation. So canonical commutation relation are really implemented in this system. And if I quotient out the ideal format by the observables vanishing on shell, namely when phi is a solution of the classical free equation of motion, I really get what's known as Borcher-Ullmann algebra. So this is the starting point of our system. And now, if I'll try to construct equilibrium state for this system, I will immediately realize that since our algebra is generated by linear field, it is enough to give the expectation value for product of linear fields. And so this product of linear fields will be described by the endpoint function of the theory, which are essentially distribution in our space-time. And in particular, if I am interested in particularly simple situation, in this case is the endpoint function of our theory in the quasi-free state can be given in terms of the two-point function only. So there are really formulas are not so important here which relate the two-point function with endpoint function. And now let's suppose to be in Minkowski space, and let's discuss how to describe the time evolution or the time translation of our observables. And the time translation of our observables is simply the pullback of the time translation of the field configuration. And now I can try to understand if equilibrium states for this system exist. And actually, it is possible to prove that if the mass is positive, it exists a unique quasi-free KMS state at inverse temperature beta. And this is the form of the two-point function given in Fourier domain. So this is nice for the free theory, but actually now there is a problem. And the first problem we have is that local fields like the interaction Lagrangian, things obtained in this way, are not contained in our algebra. And above all, if we try to compute the expectation value of this composed field in similar states, we really get divergences. And the fact that these objects are not contained in the algebra we have discussed above can also be seen because if we try to use the product rule discussed above to compute the product of two of this object, I really get divergences. So there are many divergences in the game. How can we solve this problem? And actually, this first problem in the free theory is solved by normal ordering. And the idea behind this is essentially this one. Since these divergences I am getting in computing both the expectation value and the product of this object are essentially universal. They don't really depend on the detail of the state. I can simply subtract them. And the idea is that if I have an interaction Lagrangian, which is modified by a term which is constant in the field, I expect that the dynamics is not really modified by this definition. And so this is really what I will do. I will try to subtract these divergences both from the product and from the expectation value of things. And what I will get is essentially, I will have to consider normal ordered fields. And the normal ordered fields here are given for this exponential, correspond simply to something like this form. And here, this rule of computing normal ordering is given with respect of this operator H. And this operator H has a two-point function associated with it, which is called an Hadamard function. And this Hadamard function needs to be chosen in this way. It must be a symmetric, a real B solution of this system, and there are restrictions on the wavefront set of this object. And in particular, in this restriction of the wavefront set of this object, there is a remnant of some positiveness. Actually, the covector which are assumed in the first entry of this wavefront set needs to be future directed only. But what is important is that if I select an object of this form, I really get a two-point function which has this structure. Namely, we can expand this object in this form. It is simply in the sense of distribution, u over sigma epsilon. This epsilon is just a regularization plus v log sigma plus w. This u, v, and w are smooth functions. This sigma is the geodesic distance between the 2 points associated to this two-point function, and this epsilon is really a regularization. And what is important is that the singular part of this distribution, this u over sigma plus v log sigma, is essentially universal, does not really depend on the detail, does not depend on the state. And for this reason, on a generic curved space-time, it is better to compute normal ordering with respect of this object, instead of selecting a priori a state. And having this at disposal, we can now discuss the form of the product between these two normal ordered fields. And what I get is that normal ordering really intertwines this quantum product, the product in our quantum algebra, with another product. And this other product is given here in this way. And the nice thing is that this new product I am introducing with this formula, it's really well defined also if I considered local fields. And so actually there is a bit more than this. I can really extend this new product to functional, to observables, if you like, whose functional derivative are now distribution, not smooth function as before. This this A of n are essentially related to the coefficient I was considering in previous slide. And I have just to admit some restriction on the wavefront set of this object. I have no time to discuss in detail this restriction, but what is important for us is that now the interaction Lagrangian, the local functional, are really contained in this set. And then another important observation is that the algebra constructed in this way does not really depend on H. The product constructed in this way does not really depend on H. And the last comment is that if we work in Minkowski space and if we want to compute normal ordering with respect of the Minkowski vacuum, we have simply to select H in such a way that this becomes simply the well-known delta plus. Okay, let's now pass to discuss interacting theory. And we need another ingredient here, unfortunately, and the other ingredient is the time ordering map. Namely, we need an object which takes our generator, let's say, and gives us a result element of our algebra. And this object needs to be essentially characterized by, needs to have these properties, needs to satisfy the causal factorization condition. And this condition says that if we take this time ordering of two of our observables, here F and G, and if I compute and if the support of F is not earlier than the support of G, namely the support of F does not intersect the past of the support of G, then this product here corresponds really to the star product. And this object here are functional over field configuration. So the support of this functional is defined as the regions where the observable itself is sensitive to changes in the field configuration, as you usually do with distribution, if you like. And you can really write now concrete formula for this object, and in particular on regular functional, they are completely characterized by these two things. If I try to implement this time ordering with respect of ordinary fields, I need to use this Dirac propagator. And if I want to implement this time ordering of normal order objects, I need to consider the associated Feynman propagator. This Feynman propagator is the Feynman propagator associated to the choice of this Hadamard distribution. In the case of Minkowski space, if this is chosen in such a way that I can really reconstruct delta plus, then this becomes the ordinary Feynman propagator. On the other hand, this object here is called Dirac propagator, and it is the mean of the retarded and advanced propagator. And now what happens is that I can really extend this map beyond regular functional. I can extend this map as a multi-local map, as a map from the tensor product of local functional into our algebra. And this extension is not trivial at all. Actually, we have to do renormalization here to implement this extension, and causal factorization alone does not fix this matrix completely. And actually, there are methods to construct this time ordering. And to be more precise, if we use the Epstein-Glaser method to construct this time ordering map, what I will learn is that if I want to construct T on n multilocal functional, I will actually, this causal factorization fixes it by the value of the time ordering map on k multilocal functional with k little than n. And then there is the need of extending this to some local functional. So this is not up to a local functional, and this is the place where extension of distribution enters. And of course, in this process, we all know that there are ambiguities, And nevertheless, these ambiguities are classified, and these are known as renormalization freedom of the theory. Okay, but now I think I have all the ingredients to present how to construct this interacting field. And so the idea is to select the interaction Lagrangian, something like phi of n here. And from this interaction Lagrangian, if I smear it with some cutoff, compactly supported smooth function, a cutoff function, I really get an element, one of our local functional. So the starting point is considering this potential V, this interacting potential V, or interacting Lagrangian V. And then what I will do, I will consider the time-ordered exponential constructed out of this local functional V, and I call it S of V. And this is the point, this is the place where I get really a power series. Actually, this action here will give a formal power series in the coupling constant. And what I will get is something which is only a formal power series in this coupling constant. So this S of V will be, as I said, a formal power series in this coupling constant, and all the coefficients of this power series will be decent observables in the sense I have discussed above. So this will be one of this extended, one of the elements of this extended algebra I have discussed above. Having the S matrix given in this sense at disposal, I can construct the relative S matrices in this way, and with the relative S matrices as disposal up to some sort of functional derivative, I can really get the Bogoliubov map. And this map really takes local interacting fields and gives us a result, formal power series in the algebra of free fields. And this formal power series really represents the interacting fields of our theory. It's not difficult to prove that thanks to the properties of the time ordering map, this interacting field really solves the interacting equation of motion. And now I have really a way of constructing all the interacting observables supported in O, and they are actually seen as this algebra of this algebra of formal power series, essentially generated by all possible relative S matrices where there is the interacting potential applied to every local function. So in this way, I have a way to construct, to represent at least the interacting algebra in this S formal power series with coefficient in the algebra of free fields. And now we will have to go on. We have inserted an adiabatic cutoff, which is a smooth function, and maybe this is smooth function is one on large regions, but it is of compact support. So we will have to understand how to remove this cutoff. And actually, we can do it using the following two properties. The first property I would like to use is the causal properties of the S matrix. I have this, which is the time ordered exponential of the interaction Lagrangian. And actually, it happens that if I have two local fields, two local objects, A and C, and if the support of A, the future of the support of A does not intersect the past of the support of C, I have this relation here, then this S matrix factorizes in this way. And actually, thanks to this property, I can really modify the cutoff function present in our Lagrangian without really altering anything. And actually, we can observe the following thing. If I have a local observable here depicted with this F here in this region, and if I consider two different interaction Lagrangian, which however coincide in this region colored in blue here, which is the support of F, namely the intersection of the future together with the past of our support. what happens is the following thing. I can divide this difference in two regions where this W plus is essentially supported in this orange region in this picture, while this omega minus is supported in this green region, and it happens the following thing. If I apply the Bogoliubov map constructed with V to our local functional, and I can associate to this the other Bogoliubov map applied to the interaction Lagrangian constructed with this other G+. And thanks to the causal factorization property of the S matrix, I can observe that this object here is nothing but a multiplication of this S of V together with RFV together with the inverse of this S. And actually, the nice thing is that these two objects here are unitary, and this is just the inverse of this object. And so, in some sense, up to some unitary transformation, I can really change the cutoff function present in this G. And this map constructed here can be shown to extend to an isomorphism of the algebra constructed with the cutoff function G together with the algebra of interacting field constructed with the other G prime. And actually now we can try to compute the limit G to 1 at algebraic level, and this limit G to 1 given at algebraic level becomes essentially a direct limit. So we can really give meaning to this operation. The next ingredient we need is the time slice axiom. And actually this time slice axiom says that if you have an observable of your interacting algebra defined somewhere in your space-time, you can always find another observable C contained now supported in a time slab, which is an epsilon neighborhood of a time zero Cauchy surface of our space-time up to a remainder. And this remainder vanishes on solution of the equation of motion. So it happens that if you want to compute the expectation value in a good state of your original state, of your original observable, hey, this coincides with the expectation value in this new observable C. And so if we combine this observation, and if we want to really construct a state omega for our interacting algebra, we have understood that it is sufficient to consider observables supported in this time slab of our Cauchy surface, sigma epsilon here. And so we can now specialize the cutoff in a certain way. Since our observable will be supported in this essentially orange region here in this game, I can somehow switch off the interaction smoothly in the past of this region. So I will select this time cutoff in this way, and this time cutoff will be 1 in the future of minus epsilon and will be 0 in the past of minus 2 epsilon, and it is a smooth function. And then I will add a space cutoff, which is this H. Here, this space cutoff is represented by these two lines in this picture. And now, if I want to analyze the adiabatic limit, what I really have to do is I will keep the cutoff function fixed, and I will simply take this space cutoff H and will send it to 1. This H needs to become 1. And of course, when I will exactly do like this. I will construct a state for observables supported in this region. I will keep this cutoff, and I will try to understand the limit H to 1. Of course, if eventually I will have to control how the state I have constructed depends on this cutoff function key. Okay, to do this, we want to mimic this Araki construction introduced at the beginning of this talk. So we will start to compare the free time evolution with the interacting time evolution. And actually, it happens that we have already introduced the free time evolution, and the free time evolution is the translation on a Minkowski spacetime. We restrict now to a Minkowski spacetime for simplicity. And now local fields are really translated also, even if they are interacting, they are translated by this tau of t. And so if I want to understand what's the form of the interacting time evolution, I just need to compose this relation with the Bogoliubov map. And so I learn in this way that in the interacting time evolution is defined in this way. And this is a good definition. And actually, it happens that thanks again to the causal factorization property of the S matrix, I can really connect this free time evolution, the original time evolution, with the interacting time evolution. And what happens is that the two are intertwined by some formal unitary relation. And this unitary object really satisfies the cocycle condition that they should. And in particular, I can even obtain the form of the generator of this object. And the form of the generator of this object is this one. And actually here you have the Hamiltonian density, which corresponds to the smearing in time of the interaction Lagrangian composed with the Bogoliubov map. And here you have the derivative of the time cutoff. And since our time cutoff in the picture we have seen before passes from 0 here to 1, and this means that its derivative is supported essentially in this green region depicted here. Okay, and now I have really all the ingredients to introduce the form of the equilibrium state for this interacting algebra. And actually it happens that I'll start with the free KMS state, and then I use the cocycle obtained above to construct the interacting equilibrium state a la Araki. And I will do it keeping our space cutoff fixed. And now I can try to understand what I get in this way. In this way, I really get a state, an object which does not depend on chi. This is the first important observation. This object is independent of this time cutoff chi. And now, if I'll try to compute the limit where this space cutoff tends to 1, thanks to the spatial clustering property of the two-point function associated with the KMS state, I really get finite values also in the limit where h goes to 1. And so I've really obtained in this way the candidate for being the KMS state of our perturbed dynamic. And you can really compute expectation value in this case. And you can, for example, analyze correlation function in this system. And there are really quite, maybe a bit involved, but there are explicit formulas for this object. And now a sort of list of result. In this way, Fredenhagen and Lindner have really constructed equilibrium state for the interacting theory in the adiabatic limit, namely when this cutoff is taken to 1. It is possible to extend this construction also in the case of zero masses. Recently, we have seen that a similar construction can be also done in the case of Bose-Einstein condensate. And finally, we want to compare this construction with what it is done in the physical literature. And usually one possibility present in the physical literature to describe equilibrium situation is to use what's known as the real-time formalism. And essentially this real-time formalism constructs state using the stability property I have introduced at the beginning. And so in order to use this method, we have to be sure that this return to equilibrium and the stability properties holds also for this state. And now we will see in the last part of the talk that this is not always the case. Okay, so let's start briefly to see some of this result. If we now have a space cutoff which is fixed from the beginning, and if we consider an interaction Lagrangian of this form, now if I'll take the equilibrium state for the interacting theory and I compose it with the free time evolution, like in this return to equilibrium property, and I wait long enough, I really obtain the free equilibrium state at the end. And this result can be proven essentially analyzing the decay in time of the two-point function of the free theory. Thanks to the decay in time of this two-point function, you get also in this case a sort of clustering condition. You have exactly the clustering condition we have seen before, and the proof of this theorem can be given essentially in the same way. The important thing is that this theorem works if H has compact spatial support. We have now also the way around, the opposite result. Again, if H is kept fixed, and if we now consider the free KMS state, and if we compose it with the interacting time evolution, again, if we wait long enough, we really obtain this state constructed a la Araki. And this.
Do you assume that the space-time is Minkowski?
Yes, yes, the space-time is Minkowski, but it is likely that many of these results works also on static space-time. For sure, in order to have this method, you need the following two ingredients. You need to have a space-time which is invariant under time translation. Otherwise, it is not meaningful to write equilibrium state in this system. And the second ingredient are essentially the decay property for large spatial separation of the two-point function of the free equilibrium state. And this property needs to be checked case by case. But it is likely that all these properties can be generalized also to other static spacetime.
Static spacetimes with infinite spatial
yes.
slice.
Yes. Yes, you are right. With infinite, because you need this decay property of the two-point function. If it is not infinite, then it doesn't work like this. Okay. Okay. To give a proof of this, just to give an idea of the proof of this result, what you have to do, you have to prove a sort of clustering condition of the free KMS state with respect of the interacting time evolution. And this, you have really to prove it. So you have to open the definition of this interacting time evolution. It's a bit more complicated than before. And then you have to combine all things in such a way that this kind of limit really, really works. And now, but now what we want to do, we want to see what happens in the limit where the space cutoff is really 1. And everything breaks down essentially already at the beginning. And actually, if you try to compute the limit where the space cutoff goes to 1 before the large time limit, clustering condition fails miserably already at the beginning. So you expect that no return to equilibrium holds in this case. Then you try to do some computation and you really notice that if you analyze something like this before taking the integral, you really observe that there are oscillations in this in time there. And so then to smoothen out a little bit this oscillation would be maybe good to try to compute some ergodic mean of these objects. And the idea would be to construct things like this and to take the large time limit of this ergodic mean. And again, since clustering condition fails also for these smeared quantities, no chance, no return to equilibrium is available in the limit where H goes to 1. And things are even worse than this. Actually, if you try to analyze with perturbation method, the elements of this state, you see that the higher order contribution grows polynomially in T at large time. So, so the point is that these methods in general is not really working. So you cannot really construct the equilibrium state taking just large time limit of a state constructed in this way. And This is why, to be short, this is why essentially the real-time formalism works only in special cases, only in special situations. On the other hand, the state obtained with this Araki construction is perfectly fine for every time. Okay, I think my time is almost over, so if I can steal you 5 minutes, I will just present another little point, and this other little point is the following thing. So using this method, at least when the cutoff function, the space cutoff function is compactly supported, what we really expect is that it is possible to construct equilibrium states for various time evolution. So this means we have a large class of equilibrium states and for different time evolution. And now would be nice to understand some of the thermodynamical relation among these states. And so the idea is to try to compare them using some notion of entropy. So the idea is to see if it is possible to compute relative entropy among these states. And on the market, there is already a lot of work. And for example, going back to the work of Araki, he defined relative entropy in the case of states which are normal and defined over some Hilbert space. And these are states for some von Neumann algebra. And in this way, this relative entropy is given in terms of the relative modular operator. And so the idea is to try to take this formula and try to see if you can make use of this formula in the case of perturbation theory. A direct analysis doesn't work because we don't have this relative modular operator at disposal. And so the idea is to use perturbation theory in this for W star dynamical system and to see what happens. And actually, again, looking in these cases, you can find formulas which tells you the form of this relative entropy between two of these states. And actually, this relative entropy is given in terms of the perturbation Hamiltonian P. Maybe you remember the first part of the talk. And then you need some log of n. This log of n is essentially the, this n square is essentially the relative partition function again of this system. And so the idea is to use this formula to define a relative entropy for this equilibrium state constructed for quantum field theory. And actually, this can be really done, and you can really get a maybe complicated formula, but this complicated formula has the nice property you expect for a relative entropy. And actually, surprisingly to me, this object here is really you can see that it's really quadratic in the coupling constant, and it is also quadratic in the perturbation Hamiltonian. And furthermore, it is positive in the sense of formal power series. You can also prove that similar formulas is convex both in V1 and in V2. And finally, there is some continuity in this V1 and V2. And this is the standard continuity you have in the standard topology of these perturbation things you are constructing. Okay, this is essentially all what I wanted to say. We have seen that equilibrium state can be given for quantum fields on Minkowski space-time at least. And we have seen that some stability result or return to equilibrium works if the interaction Lagrangian is compact in space. And we have seen very shortly that this is not the case when the adiabatic limit is considered, namely when the spatial cutoff is sent to infinity. And furthermore, we have seen that some relative entropy can be given to this state. So one could try to start analyzing them using some thermodynamical relation. So I wanted to thank you very much for your attention during this talk.
Thank you very much. So I'm unmuting everybody so we can clap on it. Now I'm muting back everybody. So Nicola, please immediately unmute yourself. Are there questions? So you can write them in the chat if you wish, but you can ask them directly. That's definitely better.
I have a question. What about the zero mass case?
Yes. The zero mass case is of course tricky because usually when you have zero masses, this nice decay for large spatial separation of the two-point function is lost essentially. However, for the zero mass case at thermal equilibrium, you have another fact that helps you. And this other fact is that when you consider, for example, a lambda phi to the 4 theory and you renormalize thing with respect of the KMS state, actually there is a sort of virtual mass entering in the system, entering into your Lagrangian, and this virtual mass is proportional to the square of the temperature. So you have what is known as thermal mass. So you have effectively a mass in your system, and if you consider this mass in the free theory, then you can save this infrared problem you usually have for massless theory.
So you're talking about dimension 1 plus 3.
Dimension 1 plus 3. Oh, yes. I'm in dimension 1 plus 3. Obviously.
So renormalization depends on whether you're looking at zero temperature or a positive temperature.
Yes, but all these normalization schemes can, at least outside of the adiabatic limit, can be shown to be essentially equivalent outside of the adiabatic limit.
Yeah, but you're saying that for a positive temperature, you have an effective mass that you don't have in at zero temperature. So
that's true. So, but it happens very often. No, you have at the beginning this virtual mass in the interaction Lagrangian, and now you can decide to move this mass into the free theory. So you are modifying the free theory over which you are constructing the interacting theory. And this game can be understood as a partial resummation in your system, in your perturbative system.
Okay, thank you.
Okay.
Further questions?
Yeah, I have a question.
Yes.
If you replace space-time by just a lattice, ZD,
okay.
ZD times R, right? And now you write down the same Klein-Gordon equation. How many of the difficulties are still there? For example, the ultraviolet question is no longer there, but some other difficulties are still there. And how many of the solutions survive?
Well, thank you very much for this question. And actually, the difficult part in this business is to take what's called the adiabatic limit, namely the limit where the spatial cutoff goes to 1. And I expect that if you use these lattice theories, essentially you have the same difficulties because you are looking at the large distance behavior of your correlation function. And this, I expect, even if I'm not an expert, that these are not really modified by considering the lattice theory or the ordinary quantum field theory. On the other hand, of course, when you are talking about ultraviolet problem and you consider a lattice theory, this should be completely removed from the beginning.
Thank you.
I answered the question.
Yes, you did.
Okay.
No other questions?